In part 2, we designed a system or optimized a system for average rainfall conditions. So you should feel fairly comfortable that as long as you get average rainfall, your system will meet your rainwater demands. But what if you don't get average rainfall? And that's what part 3 is all about. Also note that compared to the methodology for part 1 and part 2, part 3 is a lot more context specific and requires a lot more subjective judgment. And let me give you a quick example of this. If you're simply installing outdoor rain barrel and happy getting whatever you get, you're probably not going to need to do part 3. But if you're in an off-grid scenario where all of your indoor water demands are provided by rainwater, you're absolutely going to want to test your design, also called a stress test, at low rainfall conditions. Remember that your minimum operating goal is about the storage performance you expect in the worst case scenario that you want to design for, and that's called the minimum rain limit. And adaptive strategies are real-time behaviors or backups that can be put in place at any time. So with that, let's dive into our example. We're now on the part 3 tab. You can see that the volume and catchment areas from part 2 have been copied over to part 3. And the first thing you want to do is start your stress test. Head on over to the column called Rain Reduction Due to Drought and see what happens when you start decreasing your rainfall. You can input your percentage decrease on a month-by-month basis, or you can do what I like to do, which is to input an operator, an equal sign, and then use cell references by dragging down that operator through all months. This way, when I change one month, January, they all change at the same time. What you might input here for a reduction in rainfall depends entirely on your own context and some historical knowledge of past droughts. Before the table will populate with the month-end volumes, I need to pick my drought commencement month. Now I can look and see what has happened in my tank. The Vancouver family tests not only a 10% reduction in rain, but they also increase to a 20% reduction, a 30% reduction, and a 40% reduction to try and get a sense for their storage performance in low rainfall conditions. After performing this stress test, they decide that the performance is not acceptable, and they'd really like better assurance that they can count on their rainwater harvesting system in the 10 to 30% rainfall reduction, because they've done some research and realized that a 10 to 20 or even 10 to 30% reduction from average is really not that unrealistic for their climate. At this point, they could start iterating or back solving for how much they either need to reduce their demands by or supplement, but they skip this step because really at this point they're trying to adjust their design to meet their minimum operating goal. And because they're not meeting their minimum operating goal, they're going on to step 3.4, which is back solve, catchment, and storage. So they're going to reevaluate the size of their tank because they've already increased their catchment as much as possible. With the rain reduction due to drought set at 30%, they're going to start increasing their storage capacity until they no longer have 0 month-end volumes in the table. So their iterations have produced a tank capacity or a storage capacity of 24,300 liters. Back to our diagram. They are not really happy with that size. So they go back and do some research and decide that the absolute maximum that they're willing to purchase is a 5,000 gallon tank, or that's 18,925 liters. They don't yet want to change their minimum operating goal, so they go on to step 3.3, which is to back solve their adaptive strategies. The first thing they're going to do in their spreadsheet is input 18,925 liters, which is that maximum tank size that they are okay with. And you can see that they still have 0 month-end volumes in August and September. So now they need to start back solving the percentages in this column called adaptive strategies. And they're going to try and understand what demand volumes will result in a balanced system. But rather than iterate blindly, it's well worth looking at the month-end volumes to get a sense for where adaptive strategies are most likely to have the biggest impact. And it's quite obvious that it's in around August and September where we need to cut back on our rainwater usage. After a few iterations, they realized that 10% adaptive strategies in each June, July, August, and September result in a balanced system. So what does this mean? It means that in order to balance their system in a 30% rain reduction scenario, they have a couple of options. They could either adaptively conserve 10% of their demands, so use less by 10%. They could also supply 10% of their demands, so make up via the municipal system in their scenario. Or they can also go back to part 1 and cut out 10% of their normal operating condition demand loads. And if they had to perform any economics to figure out which decision they might take, the volume in liters is also shown on the table. The Vancouver family decided to go with the third option and go back to part 1 to cut out 10% of their normal operating conditions. In this case, they're going to lower their outdoor rainwater demand by 10%. They now have a design that doesn't require any adaptive strategies in their low rainfall condition or their rain reduction of 30%. They have a tank that they're happy with, 5,000 gallons. They figured out that they need to use both their house and their roof garage. They finally have an acceptable design, they have a solution, and they're ready to move on with all their comprehensive planning, including site layout and detailed design.